Formalizing relations and functions, take 2. So today we are going to be determining whether a relation is a function, finding the domain and range, and using function notation. So a lot of vocabulary, but all of this should be a review because this was targets from last year as well. So let's start with the warm-up. And here's a typo. So state if the equation is linear and graph the equation. So when you're looking at an equation and trying to decide if it is linear, remember that if it fits into the y equals mx plus b form, then it is linear. The other way you can look is at the independent variable, which is our x. If our independent variable has an exponent that is 1, then you know that it is linear. So yes, this is linear. So you could make a t-table to graph it, but the easiest way is remember the beginning and the move. So the b of y equals mx plus b is the y-intercept. So the y-intercept is our beginning, and the m is the move, and it's the slope. So we can start at 3, and remember this is the y-intercept, so we're starting at positive 3. And our move, our slope, is a negative 5. And because the slope is always the ratio between the change in y over the change in x, we're going to open up that basement door and put a 1 there. So that means we're going to move down 1, 2, 3, 4, 5, and over 1. Oops, I think I just went 4. 1, 2, 3, 4, 5, and over 1. And we can do that again. 1, 2, 3, 4, 5 in the negative and over 1. 1, 2, 3, 4, 5. And remember, we can also change it so the negative is in the denominator, so we could have a positive 5 and a negative 1. Either way, it turns out to be a negative 5 slope, so we could go up 5, 1, 2, 3, 4, 5, and back 1. And then drawing a line in Notability is easier than this, so bear with me. So it would look something like this. All right, let's get to some vocabulary. I think for the sake of time, I'm going to pause and type in, but then that way you can get yourself ready to write down. So if you've not opened up your notes, hopefully you have. And then you can write down the vocabulary, and I will be talking about this further in a moment. All right, so I'm going to talk through this, and you can take notes, but you might have to pause and get caught up if I'm talking too fast. So a relation is just a set of ordered pairs, and it could be in different forms. It could actually be, it looks like a set of ordered pairs. It could look like a graph. It could look like a mapping diagram. So there are different ways, but the bottom line is a relation is just a set of ordered pairs. The domain is all of the x values of any relation. So the inputs, what we're putting in. It's our independent variable. So x values, inputs of any relation is the domain. The range is all of the y values or outputs of any relation. Function notation. I'll be showing you this. This actually is a repeat from what we did in chapter 1. So you've already worked with function notation. It's just a different way of writing equations than the XY notation. It's where instead of writing the y, we name it by saying f of x. So we don't use the y, we use something like this, or many times you might see g of x or h of x. So we can name different functions using a different variable. The vertical line test is just an easy way to tell whether a graph is a function or not, using a vertical line. So again, I will be showing you that. All right, as I said, a relation could be shown as a mapping diagram. So sometimes relations are functions and sometimes they are not. If it is a function, every domain value is mapped to only one range value. In other words, every input has only one output. I suggest you add that line to your notes. Every input has only one output. So So I'll just make up some numbers here. So let's, because I'm so creative, 1, 2, 3, 4, 5, 6, 7, 8. So let's say the 1 is mapped to the 5, the 2 is mapped to the 6, the 3 is mapped to the 7, and the 4 is mapped to the 8. What this is showing us is ordered pairs. 1, my input of 1 has the output of 5 every time. The 2 has the output of 6 every time. The 3 has an output of 7 every time. And the 4 has an output of 8 every time. So there's our set of ordered pairs. So this is, yes, it is a function because every input has only one output. When we put in a 1, we know that we're going to get a 5. When we put in a 3, we know we're going to get a 7, etc., etc. So yes, every input has only one output. A relation that is not a function includes a domain value that is mapped to more than one range value. And I'll show you what I mean. Again, being so creative. 1, 2, 3, 4, 5, 6, 7. So let's say in this case, my 1 is mapped to the 5, my 2 is mapped to the 6 and to the 5, the 3 is mapped to the 7, and the 4 is mapped to the 6. Okay? Only one of these makes it not a relation, and it's this 2 right here. If we put in 1, we know we're going to get a 5. If we put in 3, we know we're going to get a 7. If we put in 4, we know we're going to get a 6. But if we put in a 2, sometimes we get a 5, and sometimes we get a 6. So this right here makes it not a function because this domain value, or this input, has more than one output. Notice it didn't matter that this output had more than one input. That doesn't make it a function or not a function. It's this one right here that makes it not a function. Every input can only have one output. All right, let's do some examples. So, the domain. The domain, remember, our inputs are x values. So I'm just going to go look at my set, my relation up here, and bring out all of the x values. And the range is all of the y values. 2.5, 6.5, and I see that I already have a 2.5, so I don't have to write that again. Now, is this a function? Well, a mapping diagram will help us determine that. So -2, 0, 4, 5, 0.5, 2.5, and 6.5. And now we're going to see which domain goes with which range. -2 went with 0.5, 0 went with 2.5, 4 went with 6.5, and 5 went with 2.5. So our question is, does every domain have only one range? Or does every input have only one output? So here the -2 only goes to 0.5, the 0 only goes to 2.5, the 4 only goes to 6.5, and the 5 only goes to 2.5. So yes, this is a function because every input has only one output. All right, being the active learners I know you are, you have this notability. So right now I'd like you to pause and try this example on your own. So pause the video, try it on your own, and then come back and check your answers. All right, so this is what I have so far. I pulled out all of my inputs, and because the 6 repeated, I only put it down once, but I also put them in numerical order. So that's just me. I like things in numerical order. If you didn't put it in numerical order, it's okay, but we like order. Mathematicians like order. So I put it in numerical order. Then I pulled out all of my y, or my outputs, 3, 4, 5, 8. Listed my domain and my range, because the next question I have to answer is it a function? And this mapping diagram will help me determine that. So the 4, I'm going to look up here, the 4 was mapped with the 3. The 5 was mapped with the 8. The 6 was mapped with the 5, but it was also mapped with the 4. So because of this one right here, because this input has 2 outputs, it is not a function. If we put in 6, we don't know for a fact what we're going to get out. Sometimes we might get a 4, sometimes we might get a 5. So my answer is no, it is not a function. The input, and I should be writing more in here, I should have a complete sentence. No, it is not a function because the input of 6 has 2 outputs. All right, let's try this vertical line test. So the vertical line test just allows us to visually see if there's more than one output for every input. In other words, if there's more than one y value for any given x value. So I'm going to take my line and I'm going to run it across. Now we can see it crosses, every time I move it, it crosses against. It's actually crossing more than once. But what we're looking at is does it cross for any given x more than once? So as I move it across, at any given place, does it cross more than once? And it doesn't. For every given x, there is only one y. So yes, this one is a function, because for every input there's only one output. So if we go to this one though, oh no, now I'm going to bring the yes with me. As I move it across, here's an x, so when x is 2, there's only one output. When x is 3, there's only one output. But here, when x is 4, there are 2 inputs. Sorry, there are 2 outputs. So when my input, I think I was saying that backwards. So when the input is 4, there are 2 outputs, 5 and 12. So because for this point right here, when our input was 4, there are 2 outputs, no, this one is not. And again, I would not just say yes or no, I'd explain it. No, for the input of 4, there's 2 outputs. And for the yes, for every input, there's only one output. All right, function notation. Like I said, we are used to seeing y notation, so xy notation. And so if you were given that problem without that f of x, you would know exactly what to do. You put in your x values to figure out what y is. That's exactly what you're doing here. You're finding the range, or your y values, for the given domain, the x. So all you're doing is plugging in each of these values, so my -2, my -1, to see what your function value is going to be for any given, or for the given x value. -7, 2, so I'm just going to plug those in and then I'm going to evaluate. So, and this is function notation, so when my x was -2, so see, instead of the x, I'm putting my -2. When x was -2, y was -4 minus 7, which was -11. When x was -1, y was -2 minus 7, which is -9. When x was 0, y was negative 7. And when x was 1, y was negative 5. So if you ever see notation like this, you can pull out those ordered pairs. Here's my ordered pair. Negative 2, my input was negative 2, and my output was negative 11. My input was negative 1, my output was negative 9, etc., etc. So my domain is what I had right there. Negative 11, negative 9, negative 7, and negative 5. That's the, and I said that backwards again. That's the range. So my domain was my x values, and the range is what I got out. All right, so this is the time that you pause, see if you can do these on your own, and then come back and check your work. All right, let's see how I did mathematically. Check yours against mine. Maybe I would have been better doing this late at night than early in the morning. So here I plugged in each of my inputs, and I got my outputs. So I just simplified to get my outputs. So here I can see that here are all my x values or input values. Here are all of my y values. So I could pull out any ordered pair that I wanted. If I had to find the slope, for example, although I see it right here, if you were working with ordered pairs, you could pull out the ordered pairs, and then here is my range. How'd we do? All right, last example. And it's a word problem, of course. John worked 3 days after school and got paid $8 an hour. He normally worked between 10 and 15 hours. What's your independent and dependent variable? So hopefully we're getting pretty good at that. What we're talking about is hours worked and being paid. So our independent, so what is being manipulated or changed, is how many hours. So our independent variable is the number of hours. So that's going to be my x. My dependent variable is the amount of money he made, or his wages. So we know that his wages, he gets $8 for every hour he works. So that's pretty easy. Now describe the domain and range. So the domain, we could just list. It says up here he works between 10 and 15 hours, so we could just list 10, 11, 12, 13, 14, 15. So we could do that list, or we could do set notation. So x is all real numbers such that x is a whole number, and it has to be greater than or equal to 10, but less than or equal to 15. So we could do it either way. And then to get the range, we're just plugging in those numbers. So I'm going to pause and do the math quick. All right, so all I did was plug in 10 for x, and 11 for x, and 12 for x, and 13 for x. Actually, I did skip counting by 8, so let me know if I added something wrong. This is the important question, though, because it's great to be able to do all of this, but if you don't know what it means, then it's kind of useless. So what does this ordered pair mean in this context? Well, you have to go back to think about what our independent and dependent variables are. Our x is the number of hours he works. So, and I'm not going to write this out, but you should. So the 11 means he worked 11 hours and made $88. So for this context, he worked 11 hours and made $88. Okay, I hope that helps you on your assignment. Make sure you ask questions as you're working through. Thanks, and we out.